This is the 28th video in a series that I'm making to support a course in elementary number theory. And here we're going to begin looking at integer partitions. So let's first look at the definition. So given a natural number n, a k-tuple, which is generally called lambda or mu or something like that, generally a Greek letter, lambda 1, lambda 2, lambda 3, up to lambda k, is called a partition of n if these two things are satisfied. So this is a non-increasing sequence. So we've got lambda 1 is bigger than or equal to lambda 2, which is bigger than or equal to lambda 3, all the way down to lambda k, which is bigger than or equal to 1. So we're not allowing negative parts or 0 as a part. And then the sum of all of these is equal to n. So we've got lambda 1 plus lambda 2 up to lambda k equals n. And just for a little bit of notation, sometimes we write lambda is a partition of n with this symbol right here. I don't really know what you call this symbol. Maybe post in the comments if you know what that symbol is called. And also, if this is a k-tuple, we say that lambda has k parts. And so this number k can vary. Okay, so let's look at some examples and then some more exotic things related to partitions, which we're not going to cover in our videos, but they're just kind of interesting to know about. So notice that 2, 1 is a partition of 3 because 3 is equal to 2 plus 1. And I want to point out that while the definition involves this k-tuple, or this ordered pair in this case, in practice, when we write partitions down, we often just write the addition problem. So we would think about this 2, 1 as the partition 2 plus 1. So 3 itself is a partition of 3. It's a partition with one part. That's because 3 is equal to 3. Then 9, 7, 1 is a partition of 17 because 17 is equal to 9 plus 7 plus 1. And just like I said before, often instead of writing this tuple here, we would write just the addition problem like this. Okay, then here is a partition with 4 parts. So 7, 5, 3, 1, that's a partition of 16 because all of those numbers add to 16. Now, when we dive into questions about partitions, you're often interested in how the parts relate to each other or the general shape of the parts. So I want to point out here that there is always a distance of 2 between adjacent parts. So that's actually a pretty common type of partition to study. So I've written that here. This has 4 total parts, and adjacent parts differ by at least 2. Okay, well, do we have a rule for this right here? And I think we do. This, maybe all of the parts of this partition are either congruent to plus minus 1 mod 8. So there are many ways, but these are 2 of the ways of looking at different types of partitions. Either the parts are in a certain residue class modulo n, or there's some difference condition on the parts. Okay, and I want to point out there are more exotic notions in integer partition theory, which we won't cover. There are things called over-partitions, and those are partitions where some of the entries have a line over them. So you can count over partitions as well as counting partitions. So notice this is 4, 3 with a line over it, 3, 2. That's called an over partition. And in this case, it's an over partition of 12. Then there are also things called colored partitions. So here, 5 is colored green, 3 is colored blue, and then 2 is colored white. And that is a colored partition of the number 10 because 5 plus 3 plus 2 is equal to 10. So before we start diving into some of the things that we would like to prove involving partitions, we need a few more definitions. So the next thing that we'll look at, which is maybe one of the most important things associated with integer partitions, is this thing called the partition function. So it's going to be a function from non-negative integers to natural numbers defined in the following way. So p evaluated at 0 is equal to 1, and then p evaluated at n is the number of partitions of n. So you might say, well, why didn't we just start this from all natural numbers to all natural numbers, so we didn't have to add this in. Well, it turns out that some of the tools that we use in order to study integer partitions, in particular generating functions, which we'll see later, really inspire us to kind of include this for the value of p of 0. Okay, well, let's look at some examples. So p of 1 equals 1. Well, I haven't written out the single partition for 1, but it's obviously just 1 equals 1. There's a single partition of length 1. And then p of 2 is 2. There are 2 partitions. There's 2 and 1 plus 1. P of 3 equals 3. So we've got 3, 2 plus 1, 1 plus 1 plus 1. And then as you can see, p of 4 is 5, and p of 5 is 7. So in fact, this number continues to grow very, very, very quickly. So p of 26, in other words, the number of partitions of 26 is 2,436. And then the number of partitions of 300 is this very, very large number. So let's see. 1,000, million, billion, trillion, quadrillion. It's like on the order of a quintillion, or 9 quintillion, I should say. Okay, so now that we've got this very important function and some examples of this function, you might ask, is there a formula for this function? And there is, but it's really hard to work with. So let's see maybe part of that formula on the next board. So Hardy and Ramanujan found a formula for p of n, but it's expressed as an infinite series. That being said, this infinite series converges very, very quickly. But on the other hand, the terms from this infinite series are really quite difficult to look at. So this is the very first term of the infinite series that these guys came up with for p of n. So let's see what we've got. 1 over 2 pi times the square root of 2, the derivative with respect to n of this object. So we've got an exponential function in the numerator, 2 pi over, that should be the square root of 6 here, and then the square root of n minus 1 over 24, and then another one of those in the denominator. So as you can see, there's lots of parts of this object that are not natural numbers, but when you put all of this together and look at the infinite series, then you will in fact get a natural number. Okay, so the next thing I'd like to talk about is what are some interesting questions we could ask and answer about integer partitions. So let's see that. So now we're going to look at some typical questions which you might see in integer partition problems. But just before we do that, we need to look at the notion of a restricted partition. So these are partitions of n satisfying certain rules. We hinted towards some of these at the very beginning of the video when we looked at our very first examples of partitions. So here I've got 6 examples of restricted partitions. So maybe all of the parts are odd. So that means all of these lambdas are odd. All of the parts are distinct. So that would erase the possibility of having equality here. The parts are odd and distinct. So that's just putting these 2 restrictions together. There are at most m parts. So that means this k would be less than or equal to m. The parts are congruent to plus minus 1 mod 5, or maybe plus minus 2 mod 5, or maybe plus minus 3 mod 8, or so on and so forth. In other words, the residue classes of the parts. Or the adjacent parts differ by at least 2. So that means between lambda 1 and lambda 2, there's at least a difference of 2. Same thing, lambda 2 and lambda 3. That would be this last restriction. So the big question is, when does the number of partitions with one restriction equal the number of partitions with a different restriction? So you may or may not have heard of the Rogers-Ramanujan identities, and those actually give us some sort of relation between parts that are congruent to plus minus 1 mod 5 and partitions where the adjacent parts differ by at least 2. Furthermore, there's a nice relation which we'll see later, maybe not in this video, but in an upcoming video, comparing partitions where the parts are odd to partitions where the parts are distinct. So next, we're going to look at a nice graphical tool for analyzing integer partitions. Now we're going to look at an important graphical tool for studying integer partitions. These are called Ferrers diagrams. So if we've got a partition lambda of n, we'll just say lambda has k parts like this over here. The Ferrers diagram is a diagram of n dots laid out in k rows. So the first row has lambda 1 dots. The second row has lambda 2 dots. The third row has lambda 3 dots, all the way down to the kth row, which has lambda k dots. Furthermore, we push all of the rows all the way to the left. So generally there's like this kind of shape right here in the diagram. There's like this overhang at the left-hand side. Okay, now the next thing that we want to look at is the notion of a conjugate partition. And that's really built off of some of the graphical stuff in the Ferrers diagram and some symmetry. So the conjugate partition, which we call lambda transpose maybe, is formed from reading the Ferrers diagram column-wise. So instead of starting with lambda 1, we would have these dots are forming the first part. So let's just see right here. So lambda transpose in our case will begin with k because we're reading this first column and we know this first column has k entries because there were k parts to our original partition. But then all bets are off after that. Another thing that I want to notice is that there's like some sort of geometric transformation that we can do to this Ferrers diagram to turn it into the Ferrers diagram for the conjugate partition. And that is we take a diagonal down these dots right here, and then we'll do a reflection. And that will reflect a Ferrers diagram for a partition into the Ferrers diagram for the conjugate partition. So let's see some examples of that. So here are a few examples, which I think are nice illustrations of this notion of a conjugate partition, along with the original notion of a Ferrers diagram. So here we've got the partition 3, 2, 2, 1. So let's notice that we've got 3 plus 2 plus 2 plus 1. So that's going to be 8. So this is a partition of 8. Its Ferrers diagram looks like this. We've got 3 dots in the first row, 2 dots on the next 2 rows, and then 1 dot on the last row. So this has 4 parts. Okay, so let's look at the conjugate partition. So we're going to do this like graphical transformation. So we're going to put a diagonal down here and think about doing this reflection. So let's see what that's going to give us. That's going to take this first column and whip it up to the first row. So we'll have 4 dots on the first row like this. Then we'll have 3 dots on the second row. And then finally, we'll have 1 dot on the last row. And if we put this red line back, we can see that, yeah, we did create the appropriate reflection translation. Now we can read off this diagram and know what the conjugate partition is. So it will be 4, 3, 1. So 4 plus 3 plus 1. Now, if you were to write that in terms of tuples and conjugate, you would maybe write something like this. 3, 2, 2, 1 conjugate or transpose equals 4, 3, 1. And likewise, the transpose is like a dual action. If we were to do it again, we would land back up here. So 4, 3, 1 transpose or conjugate is 3, 2, 2, 1. Okay, so now let's look at the rest of these. We've got the partition of 4, which is just 4. So let's put our diagonal in and let's do our reflection. So notice that's going to give this first row, which is only a single row, into a single column. So we've got this right here. And so that's obviously the partition 1 plus 1 plus 1 plus 1. Now, if we were to write this in terms of our tuple notation and our conjugate, we would have the partition 4 conjugate is 1, 1, 1, 1, like that. Okay, and then likewise, the partition 1 plus 1 plus 1, if we reflect it like this, will turn into the partition 3, because that's just going to give us 3 dots like this. And then that would have a similar representation in terms of our tuples like this one right here. Now let's see what happens to this partition 2 plus 2, which is a partition of 4. So notice if we put our line there and then do our reflection, nothing happens. That gives us exactly the same Ferrers diagram. but that means that the conjugate partition is equal to the original partition. So we've got 2 comma 2 conjugate is equal to 2 comma 2. This is what's known as a self-conjugate partition. So all self-conjugate partitions are those that when you take their conjugate, you just get themselves. And this notion of a self-conjugate partition will actually motivate one of the problems that we'll do in class, if you're in the class that I'm teaching related to this material. Okay, so let's look at our first big theorem involving integer partitions. So here's our first big theorem involving integer partitions. So we want to consider the following classes of restricted partitions and a partition function like this related to those restrictions. So P sub m of n is equal to the number of partitions of n with less than or equal to m parts. That means it could have 1 part, 2 part, 3 parts, all the way up to m parts. And then pi sub m of n is equal to the number of partitions of n with parts that are all less than or equal to m. Then for all natural numbers m and n, Pmn is equal to pi mn. Before we look at a proof, let's look at an example to get an idea for how this might work. So let's say n equals 6 and m equals 2. So that means P2, 6, we'll be counting the number of partitions of 6 with 1 or 2 parts. That's because we've got less than or equal to 2 parts. Well, there's a single partition with 1 part, that's 6. 5 plus 1, 4 plus 2, and 3 plus 3 all have 2 parts. Okay, then pi 2, 6 will be counting the number of partitions of 6 where we're only allowed to use the number 1 and 2. So notice 1 plus 1 plus 1 plus 1 plus 1 plus 1 is maybe one of the simplest ones to think of. And then you have 2 with a bunch of 1s, 2 plus 2 plus 1 plus 1, and then finally 2 plus 2 plus 2. Those are all our partitions in that case. So as you can see, we have 4 partitions of this class and 4 of this class, and 4 is equal to 4, so we're good to go. But we might look at this and see, well, what is the relation between these partitions? And it's not too hard to see that the relation between these partitions is most obvious looking at the Ferrers diagrams. So if we take the conjugate of this partition, 3 plus 3, we end up with this partition, 2 plus 2 plus 2, which, like I said, is easy to see via the Ferrers diagram. Furthermore, if we take the conjugate from here, we get back up to here. So that provides a link between those two partitions. Furthermore, the conjugate of this guy is equal to this guy and vice versa. The conjugate of 5 plus 1 is the conjugate of this 2 with some 1s. And finally, the conjugate of 6 is equal to the partition with all 1s. And again, all of that is pretty clear just from what happens with the folding in the Ferrers diagram. Okay, so now motivated by this example, let's look at a proof. Okay, taking motivation from our example, let's dive into a careful proof. So let's define two sets. We'll define the set AK. So this is going to be all partitions of n with exactly k parts. And then we'll define BK to be equal to all partitions of n with largest part equal to k. And next, I want to notice that those are going to be related to these functions in the following way. So notice that Pm of n will be equal to the size of A1 union A2 all the way up to Am. Those are disjoint sets as well. So maybe I'll put a little dot here to show that we're doing a disjoint union. And furthermore, pi m of n will be the number of elements in B1 union B2 union all the way up to Bm. Again, those are disjoint unions. That's because here we want less than or equal to m parts. So this would be exactly m parts. The one right below it would be m minus 1 parts. All the way down, this would be 1 part. And then here, we want partitions with parts less than or equal to m. We'll notice that the largest term in the partition governs the size of the rest of them. So if we define BK like this, then it's pretty clear when we take this union, we're getting that type of set. So next, what we want to do is define a function which will be a bijection between this type of set and this type of set. So we're going to define f from AK to BK by lambda turns into lambda conjugate. And now we really need to prove that if we start with a lambda in AK, lambda conjugate really is in BK, just so that we know we have the right codomain here. So let's maybe make that a claim within the proof. So if lambda is in A sub k, then f of lambda, which is lambda conjugate, is in B sub k. Okay, so let's see if we can look at the little proof of that claim, and we'll use the Ferrers diagram for that proof. So let's suppose that lambda is in A sub k. What does that mean? That means lambda has exactly k parts. So we could draw the Ferrers diagram for lambda. Let's do that. So it'll look like this. We'll have lambda 1 dots in the first row, lambda 2 dots in the second row, all the way down to lambda k dots in the kth row. And the important thing here is that there are exactly k parts. That's because we came from AK. But now let's apply our conjugate function, which we called f. Notice that's going to give us lambda conjugate. That will do the reflection, which we've been using all the time. So that's going to reflect this column up to a row. So we have something like this, but that represents our largest part, which is the first part. And it's pretty clear that this is k, because the number of parts becomes the largest part in the conjugate. And then we've got some parts down here as well, but those don't matter so much. So that's admittedly a bit of a sketch of the proof, but I think that's sufficient for our setup. Okay, another thing that we want to notice is that this function is its own inverse. So if lambda, or maybe we'll call it mu, is in B sub k, then mu transpose is in A sub k. So that means not only is f going in this direction, but f is also going back in this direction as well. And then you can prove this via the same kind of strategy that we did over here. Okay, so let's maybe take those facts and we're ready to finish this proof off. On the last board, we set up some sets AK and BK, as well as a function between them. So this function goes in both directions. And what it does is it takes a partition and gives you the conjugate of the partition. So let's maybe note real quick that if we do f composed with f inverse of lambda, we get lambda conjugate conjugate. But it's pretty clear that if we take the conjugate of the conjugate partition, we get back to the original partition. So what that means is that f is its own inverse. But just the fact that it has an inverse, not even that it's its own inverse, but the fact that it has an inverse means that f is bijective. Okay, but if f is bijective, that means the number of elements in AK is equal to the number of elements in BK. And now we're pretty much ready to do it. So let's notice that PM of n is equal to the size of A1 union up to AM, which is equal to the size of A1 plus the size of A2 all the way up to the size of AM, because those are disjoint sets. But that's equal to the size of B1 plus all the way up to the size of BM from what we just showed. But that's equal to the size of B1 union all the way up to BM, again, because those are disjoint sets. But that was just another way of counting pi mn. And so looking at the extreme left and right-hand side, we see that we have built the equality that we wanted to. Okay, so let's finish this video off with a couple of warm-up problems and then we'll be done. So here's some warm-up problems based on what we just did. So write all of the partitions for 6 and 7. So this might be close to the largest numbers where this is a reasonable exercise. It's probably still reasonable for 8, 9, and 10, but just not very fun. Okay, next, draw the Ferrers diagrams and find the conjugate partitions for each of these partitions. So we've got 5, 3, 2, 2, 1, 1, 1, and 7, 7, 5, 3, 2. Next, just maybe look on the internet and read something about Ramanujan. Maybe if you're in my class, be ready to talk a little bit about what you read in class next time. And that's a good place to stop.